Hi, my name is Rebecca and welcome to my talk. In this video I will present a joint work with Benjamin Cabrera, Reiko Heckel and Barbara König. The title of our paper is Uncertainty Reasoning for Probabilistic Patronets via Bayesian Networks, where we have incomplete knowledge about the state of a system and gain more information by observing probabilistic transitions. But first let's have a look at some motivation and why we think that this research is valuable. Let's say we have a very large network, for example, a social network with a lot of people in it, and these people are connected to each other and can send messages. Now let's assume that there is a piece of information among the network users, and we as an uninvolved observer want to find out who has knowledge about this information. The information, of course, can be spread by the people, and we can observe when a person sends a message, but we cannot see whom the message is addressed to. However, we might have some probabilistic knowledge about who could be the recipient based on some prior knowledge. If Amy sends a message and she's better friends with Bob than Carl, it is more likely that this message was addressed to Bob. The more transitions we observe, the more information we gather about the system state, which in our case is who is aware of this piece of information. What we now have is a dynamic system in which we know the structure but have incomplete knowledge about its state. Furthermore, we observe probabilistic information that not only gives us more intel on the current system state, but is also capable of changing it. According to this information, we must update our knowledge accordingly, and finally reason about the probabilities in order to answer a question about the state. For example, how likely is it that Carl knows this information now? So what we need is a way to efficiently store probability distributions. We need an update mechanism for this new incoming probabilistic information, and at the end we need a suitable evaluation mechanism. This talk is structured into three main parts, where the first part discusses the dynamic system we chose to observe, the second part explains how we can efficiently store and update the probabilistic knowledge on this dynamic system, and finally I will talk about how we can draw conclusions from the probability network. The arrow below illustrates that we observe transitions with probabilities on the dynamic system and then incorporate this information into our knowledge representation. So let's start with the dynamic system we observe. We chose condition event nets with uncertainty here, and basically condition event nets are Petri nets with the restriction that every place can have only up to one token. This limits the whole network to a binary system as every place is either marked or empty. Now let's look at a minimal example where we have a social network with 3 people. There are certain transitions that illustrate the information being spread, and we assume that we know about the whole structure of the system. If a place is marked, that means that the designated person knows about the information. Initially, we have some prior knowledge about who knows the information in form of a probability distribution over all possible states represented in a table. As you can see here, the probability that everyone is already aware of the information is 1/12. The probability that nobody knows is 1/8, and so forth. In our assumption, we therefore know the network structure but have incomplete knowledge about the marking in form of a probability distribution. Okay, now let's do an example. Say we just observed that person 1 sent a message to either person 2 or 3, and that person 1 is better friends with person 2. Therefore, the probability for the first spread transition is twice as high as the second transition. The third transition is 0 as it doesn't have person 1 as a precondition. Now we want to update our state assumption by incorporating this new knowledge. When thinking about state changes with probabilities, a familiar concept comes to mind, namely Markov chains. As a matter of fact, we can easily translate this scenario into a Markov chain. We have all of the possible states as the vertices, and the edge labels represent how likely a state change is depending on the probabilities on the left side. For the sake of completeness, we introduce a fail state that collects all edges from states that are not possible anymore, namely all states in which person 1 is not aware of the information. This Markov chain now accurately depicts the transition probabilities, and in order to calculate our updated state knowledge, we simply have to multiply the initial distribution with the Markov chain matrix. This generates the correct new state distribution. However, there are some problems with this method. First of all, the probabilities can change in every step, which would mean that we had to create a new matrix for every transition. Furthermore, the matrix dimensions are of exponential size, making this method scale very badly. Suppose the network is bigger and we have 20 people in it, and the matrix dimension would be of 2 to the power of 20, and the update mechanism would be very inefficient. However, not all hope is lost here, because usually we only observe local changes. Not all people in a network are going to be connected, and based on the given structure of the conditional event net, we can narrow down the number of people involved in an observed transition. In order to follow through with our idea of local updates with smaller matrices, we have to somehow split the initial probability distribution such that we obtain smaller tables. As a solution, we chose a modification on Bayesian networks called modular Bayesian networks. After making this decision, let's have a look at how to transform a joint distribution table into a Bayesian network. Now, there are two types of variables in a Bayesian network: independent and dependent variables. The value of an independent variable is not depending on any other variable, whereas the value of a dependent variable is depending on the value of at least one other variable. In this example, you can see that the first 4 probability values are the same as the last 4. This implies that S1 is totally independent from the rest of the variables. S2 and S3, however, are dependent on each other. Here, we choose that S3 was dependent on S2, but this is an arbitrary choice. So now this Bayesian net represents the same probability distribution as the table on the left, but it needs less space to store and it's more split up, which gives us the local component that we were looking for. So now we ended the first part of the talk and addressed the probability framework that we use in order to represent and update our knowledge about the state. I just explained how we can translate a joint distribution into a Bayesian network, but now we face the problem of an update mechanism. Ordinary Bayesian networks are not made for any extensions or changes overall, but because we observe a dynamic system, we have to be able to update our network. And for that, we just use modular Bayesian networks, which actually allow add-ons through their compositionality. With this modification to normal Bayesian networks, one can actually have smaller networks and stick them together to obtain a bigger network. This also fulfills our locality requirement. So first of all, we have our normal Bayesian network that we just created on the left side, and because we're using some kind of local Markov chain, we should be working with matrices. The right side depicts the same Bayesian network, only the information is formatted in matrices here. The core idea of a modular Bayesian network is that it can take an old network as input, add changes to it, and thus create an updated version where any new information is now incorporated. This can be understood as some sort of timeline. As can be seen here, our timeline goes from left to right, meaning vertices on the right are only influenced by vertices on the left. In an ordinary Bayesian network, every variable is assigned to a specific vertex in the network, but because in MBNs we can add vertices and take old vertices as input, the variables are all on the right side and have a designated wire. These wires can be set to any value, and since we are investigating the binary case, a wire can only be set to either 1 or 0. In our example, the wire of S3 is attached to a 2 times 2 matrix. This matrix has one input wire, which is the same one that is assigned to S2. This reflects our choice of making S3 dependent on S2. After obtaining an MBN, the new question now becomes, how do I evaluate this network? Meaning, how can I calculate the joint distribution from this representation? The answer to this question is actually fairly easy. Every output wire attached to a variable gets assigned either value 1 or 0. Then we have a look in the matrices and choose the entry that corresponds to the wire assignment. We take these probabilities, multiply them, and done! We now have the probability for one possible state. Now this process has to be repeated for all possible states. In this example, we start with every variable set to 1 and we take the designated matrix entries. The same goes for the second possible state, where we now change the assignment of S3 and so on. Now, only wires attached to a variable get assigned a specific value. For all free wires, we have to iterate over all possible assignments, look up the designated table entries of all nodes, and multiply the values together. After doing that for all possible assignments, we add up the products and continue with the next state. This means that the more wires we have, the more operations we have to do when evaluating the network, namely every added wire doubles the amount of operations. Okay, so this is how you can evaluate the network, but how does it look like when we update it? Let's take the example from before, where all 3 people were involved in the transition because person 1 either sent the message to person 2 or 3. This means that the new node is dependent on all 3 variables and should take all of them as inputs. P prime is basically the same matrix as P before. We just have to rearrange the values a bit to fit the Bayesian network style. Now this doesn't really look like it's more efficient because the matrix is of the same size as the one in the Markov chain, but this is only because the condition event net is really small. In this example, we added one more place to the condition event net that is not affected by the observed transition. The efficiency improvement is now visible as matrix P prime is smaller than the Markov chain matrix would be, because it doesn't incorporate S4. This improvement stems from our knowledge about the condition event net structure, enabling local updates rather than global ones. The depiction of MBNs here is called string diagrams, and they are based on the theory of CC structured props. On the basis of CC structured props, string diagrams can be translated into terms and serve as a way of providing the correctness of our method. Now, let's start with the final part of my talk concerning the efficient evaluation of MBNs. In our overview, this means that we have a modular Bayesian network that we incorporated observed updates into and now pose the question, how can I reason about specific places in the condition event net? So first of all, we want to compute marginals. This means that we're not interested in the joint distribution, but in the probability of one specific variable. In our example, we want to compute the likelihood of person 3 possessing the information. In order to do that, we have to get rid of the other variables, and in string diagrams, we can just terminate wires we do not want to use anymore. A wire termination is basically just adding on a specific matrix, namely a matrix that takes one wire input but doesn't forward the information anymore. So if we terminate the wires of S1 and S2 and evaluate the network as is, we would compute the marginals of S3. Now, when evaluating a network, this can be done more or less efficient. A well-known method for computing marginals in a Bayesian network is the so-called elimination order method. Here, nodes will be merged together by evaluating small parts of the network after each other in order to keep the newly generated matrices as small as possible. Now, let's first look at a bad elimination order. The measure used here is the number of evaluated wires. As shown before, this number should be as low as possible to gain the best elimination order. In the bad example, we first choose matrix D and E to merge together. In order to do that, we have to take all wires attached to D and or E and iterate over all wire assignments. When choosing D and E, we simultaneously choose all vertices because they all have a wire connected to either D or E. When evaluating the whole network at once, we would need 2 to the power of 5 permutations for the wire assignments because the values, once again, are binary. Now, this number can actually be split in half only by choosing a different elimination order. Let's first take the nodes A, B, and D and evaluate the partial network such that A, B, and D collapse into one vertex. This costs us 3 wires and leaves us with 3 wires remaining to evaluate, so in total this elimination order only has 2 to the power of 4 permutations. This makes clear that in order to efficiently evaluate a Bayesian network, we need a good elimination order, but how do we get one? Now, this is where we use tree decompositions. In order to find a tree decomposition for a Bayesian network, we first have to moralize the network. Here we forget about the edge directions and connect all parents of a node. Now we have a graph for which we can find tree decompositions. For our graph, there are 2 valid tree decompositions and they correspond to both the bad and the good elimination order. The goal of a tree decomposition is to rearrange the graph by putting nodes together in bags such that we obtain a tree structure. The first tree decomposition simply puts all variables into one big bag, acquiring the most basic tree. This actually generates the bad elimination order because there is no real ordering, we just evaluate all nodes at the same time. The second tree decomposition, however, puts A, B, and D into one bag and C, D, and E in another one. This still is a tree structure, but we evaluate the network in 2 steps now. The best tree decomposition is the one with the smallest bag overall and is needed in order to generate the best elimination order. The problem here is now that getting the ideal tree decomposition is actually an NP-hard problem. For our implementation, this means that we can only approximate the best elimination order by implementing 2 different modes. The first one looks through all node pairs and calculates how big the matrix would be if we were to merge these nodes, and then takes the pair that would generate the smallest matrix. In the second mode, we simply count the involved wires, aiming for the lowest number possible. Both of these modes are very similar in choosing an evaluation order, and so far we couldn't find any relevant efficiency differences. We also added some local optimizations, for example, getting rid of nodes without output first and nodes without input second. As already mentioned, we have a running implementation of our theory, and this plot shows our runtime results when compared to the joint distribution method, which is based on the probability table from the beginning. In our simulation, we generate condition event nets with a certain amount of states, random transitions with up to 3 pre- and post-conditions, and random markings. Then we execute 10 steps, where each step has up to 5 randomly chosen transitions, assigned with randomly chosen probability values. All the other transitions get assigned a 0 probability. Then after executing 10 steps, we evaluate the network by calculating the marginal probability of one randomly chosen place. Here we compare the runtime results in their median, and as you can see, the joint distribution approach scales exponentially, whereas the MBN approach stays somewhat linear. Now, this plot shows the correlation between the number of wires on the largest matrix in the MBN and runtime it took to update and evaluate the network. As you can see, this does not really correlate with the number of places in the condition event net, making the MBN approach actually scalable even for larger networks. For the joint distribution approach, the storage demand when initializing a condition event net with 30 places was already so high that we couldn't even start the simulation. Of course, when the added matrices get so big that the advantage of local updates is no longer given, the MBN approach does not run faster. So, in conclusion, we developed a framework based on Petri nets in order to accomplish uncertainty reasoning based on time in homogeneous Markov chains. We also used modular Bayesian networks to symbolically represent probability distributions as well as update them. Furthermore, we modified the variable elimination method for modular Bayesian networks and used this method to efficiently compute marginals. Finally, we developed a running implementation available open source on GitHub that showed an improved performance for our theory. For future work, we would like to investigate how completely unobservable transitions should be handled in our framework, as well as move into a more user-oriented direction. Right now, our system only observes but cannot engage with the transitions, which could be extended by transitions controllable by a user. We are also interested in investigating different system types outside of condition event nets and having a closer look at continuous time Markov chains and Markov decision processes. Thank you for your attention. I hope that I will see you in my Q&A session.